Welcome to a lesson with Dr. Powell. Let's take a look at finding the average value of a function with three inputs and some of the applications of it. Okay, first of all, function has three inputs. That means that its inputs can range in terms of x, y, and z coordinates. It can be anything in space in 3 dimensions for the input. So if we're finding the average value of a function over a part of the domain, let's consider just like a region or a shape or a solid or mass or something in space that has some kind of depth and body to it. And suppose we have a function f, x, y, z, and we're considering this three-dimensional region here, and we want to find the average value of it on it. Now, analogous to what we've done before, it's simply done by taking 1 over the volume of that region, and then you just look at the integral of fx, yz, dx, dy, dz over that region. This right here would compute the average value of the function. So just even comparing to the case of a function of a single variable, just in reflection, we have if we find the area under a curve and we divide by the length or the measure of the domain, we get the average value. So area divided by measure of domain. So here, literally, the volume of R is like the measure of domain. We divide by it and we take the integral. So, and the area here would be an integral, but here we're, like, well, what is this? I mean, if you kind of beefed up to 4 dimensions somehow, but we're not going to visualize that, but we still carry the same idea over. This is how we compute the average value of a function with 3 inputs. What are some applications of this? Well, if we want to think about finding something like a center of mass, but first, maybe let's simplify and let's think about mass as being uniformly distributed. And so kind of like center, like maybe we're thinking of a geometric type center where of a shape, a solid. How do we do that? Well, we have an x coordinate and a y coordinate and a z coordinate. We want to find kind of a center coordinate for the shape where volume is kind of acting as mass. So the more volume there is, the more mass there is. In that sense, we kind of get a geometric center called a centroid. So how would that work? Well, basically, we want to find the average value of x. Let's just let our function be x. We want to find the average value of this function. So simply, we just compute this and divide by the volume of the region, and we're done. This right here computes x bar. Similarly, to do y bar, we can do the same thing. Just replace that x with a y. To compute z, we do the exact same. Replace that with a z, where we compute just the average values of these things, of these things as functions over this input, where we're kind of, our range of inputs is over the whole volume. Now, when we are working with finding x bar and y bar, and we're working with a single variable, we have to kind of finagle things a little bit more, because we want to figure out what the center x value is with respect to area. When we're only integrating in one direction, one thing, we're actually integrating 1/2 of a double integral, or we kind of have to do some kind of substitution or whatever variables to make this work right. But now, since we've beefed up to multivariables, we have a much more natural setting in which to view X bar, Y bar, and Z bar. So if we want to find the center of mass in space, in a three-dimensional space, this is what we would do. If we want to find the geometric center, X bar and Y bar of something just in the plane, we can do something similar with double integrals. To find X bar, you do the same thing. Here we have that, and here dv was, you could think of dv as being dx, dy, dz in that case. Just labeled it as dv, but really you could think of that. Here you could say dA, or you could say dx, dy, and then you just say 1 over the area of the region. I mean, this would work too, this type of thing, if you're finding X bar. So it's just is a question of if it's two-dimensional versus if it's three-dimensional for the input. The same basic thing works even for one dimension, but you only have one variable then here. In that case, here you have X bar and Y bar. For one dimension, you would have it would just be X, and it would just be a straight line. And the geometric center is very easy. It's just the average value in the middle, but it could still be done in the same way. In the same basic way. For instance, if we had X dx and we're going over an interval from like 0 to 5, say, but then we want to divide by, and then we divide by, let's see, the input for this particular function has measure a fifth. And so kind of thinking about this going along to find the geometric center, we do this x squared over 2, go from 0 to 5, and multiply by a fifth. But notice what happens in the process. You end up just getting 5 over 2, which is just 1/2 of 5, the geometric center. So really the same idea holds from 1 dimension, 2 dimensions, 3 dimensions. You're just finding the average value of x and y versus x here, x, y, or z. So kind of this basic idea of finding geometric center of the centroid. We could even think about cases where perhaps mass is not distributed uniformly. Then we'd have center of mass. Suppose that the mass density itself changes in space. And let's just think about the three-dimensional case. Let's let delta correspond, the Greek letter delta, correspond to a function with 3 inputs, and the output is the current density of mass. That means at this particular point, maybe the mass is like 5 kilograms per square, per cubic meter, or something like that. That'd be very light, or per cubic foot, or something like that. You could definitely use something like this to help you out with density. And all you do is you multiply your density by how much volume, meaning like your dv or dx, dy, dz, a little piece of volume. Take a little piece of volume and multiply it by the density, and guess what we have? We have the mass, or the little piece of mass, call it dm, at that particular piece of volume, dv. At a particular dv, you have your dm, and all you have to do is just throw in a function here, a delta function, delta x, y, z, multiply to that, and that would give it to you. So how would things change? Well, essentially what this is, you'd be finding the average value of the function x, but not with respect to volume, but rather with respect to mass. And then what do? You divide by the total mass, just like you would do the total volume, but kind of change a variable from v to m, say. It's the same basic type of idea. Here we have 1 over mass, and then we have x dv right here. So in this case, we get something very nice, finding the average value with respect to mass. And it's basically the same thing. You just replace your V's with M's and you get center of mass. Here, this would be the X coordinate of the center of mass, just finding the average value of X with respect to mass now. Where dm is simply just maybe something right here, some function in 3 variables multiplied times your dv. So we'll look at some examples of making these computations in the next video, at least one computation in the next video that follows. Thanks for watching.